Okay, so the last installment of topic 4 questions. Question 36 is the last one before the summary test on this particular set of questions. So let's get onto it and see if I can finish it nice and quickly for you. So the enthalpy of a reaction between magnesium metal and hydrochloric acid was to be quantified in a laboratory. So then a 0.1277 gram piece of magnesium ribbon was added to 200.0 milliliters of 0.500 moles per liter HCl at 24.12 degrees Celsius. The water temperature increased to 27.10 degrees Celsius. So it says calculate the enthalpy change for this reaction. So the first thing I'm going to do, actually I probably don't even need to, but I'm going to do it anyway, is I'm going to write down the reaction between magnesium metal plus HCl becomes, so I'm pretty sure it becomes MgCl2 plus H2. So magnesium becomes Mg2 plus, and obviously chloride Cl is Cl minus, so I need two of those, and I make hydrogen gas. Now this is not balanced, so we need to put a 2 there. So I think that's pretty much it. Now, I'm not sure if we'll need to use it, but sometimes you would to be able to convert from the stoichiometry of this to this. So for every one magnesium mole of magnesium, we need 2 moles of HCl to react with it. So moving on, it says calculate the enthalpy change for this reaction. So like always, we need to look at the water first. So the energy change of the water. Now, before we start, I'm going to try and identify what I expect to see. So for example, the positive or negative. The water has increased from 24.12 to 27.10, so that shows an increase in temperature, so the water has absorbed energy. So mass times C times delta T is equal to the mass of the water is 200 mils, so 200.0 grams, times by our C, which is 4.18, not grams, joules per gram per degree C, times by our delta T, which is a change from an increase from 24.12 to 27.10. Now, if it was 24.10 to 27.10, it would be 3 degrees. Now it's 0.02 less, so 2.98 degrees C is our change. Okay, throwing that into the calculator. So we go 200 times 4.18 times 2.98 is equal to 2491.28 joules, and that's a positive value because of our positive temperature. So normally I wouldn't bother with a positive and negative, positive if it is just a positive number, but I want to be really clear that our water is absorbing that energy, which means it's being lost by our reaction. So the Q of our reaction is equal to the negative Q of our water, or actually technically it's the negative Q of the surroundings, which is equal to negative 2491.28 joules. Now the enthalpy change, like usual, so we go, now delta H is equal to Q of our reaction divided by N, and our N is equal to, so that's for our magnesium ribbon, which is mass, which is 0.1277 grams, divided by the molar mass of magnesium, which looking at the periodic table gives us 24.305. 24.305 grams per mole gives us, putting that into the calculator as well, 0.1277 divided by 24.305 gives us 0.00525 moles, which I will replace as 5.254 moles, times 10 to the negative 3 moles. Now, again, that's not my final answer. My final answer is going to have 3 significant... Oh, actually, no, that's not what I need to do. Oh, actually, you know what? I think there might be an extra step that I may need to do. We'll see. We'll see in a second. So, I'm just going to pretend. I'm going to continue pretending for the moment that I knew, or I know that all the magnesium will dissolve, will react with our HCl. But that's not necessarily the case. One of them could be, or the hydrochloric acid could be limiting, but we'll find that in a minute. So the number of moles of our magnesium, I'm going to make this really clear, is that number there. Now, the number of moles of HCl is equal to N equals C times V. The concentration is 0.500 molar times by our volume, which is 0.2 liters, and that is equal to 0.1 moles. Now, 0.1 moles of this will react with half as many moles of magnesium, which would be 0.05. We have a lot less magnesium. So that means magnesium is our limiting, so we should go with the number of moles of magnesium here. There is plenty of hydrochloric acid to react with the magnesium we have, so the limiting thing is the magnesium, and that's what we're going to go with for our N. So our number of moles of magnesium there. So our delta H is going to be our Q of our reaction, which is negative, so it'll be 2491.28 divided by our 0.005254, giving us negative 474.168. That is not clear at all. Negative 474.168 joules per mole, which will be negative 474.168 kilojoules per mole. And the last step, which is 4 significant figures there. Our change has 3. Our heat capacity has 3. So we're going to use 3 significant figures, which will be negative 474 kilojoules per mole. Cool. There's our answer. Now it says describe what assumptions are made in calorimetry. There's probably a few of them. I'm going to go through a couple. Now, one thing to know is that when it says the temperature, when we're looking at the temperature of our water, you need to assume that the whole vessel has the same heat capacity as water. So if we look up at our image up here, where are we? So if we look up here, we have a glass stirrer, which is inside. We have a thermometer, which is inside. Both of those are going to absorb some energy. So even though we're assuming that it's all water in here, the cup is going to absorb some energy, the glass is going to absorb energy, the thermometer will absorb some energy. So yeah, again, we're assuming that all of it has the same heat capacity, which is not exactly true, but we're going to assume that anyway. And once you look at that, they're also they've also written them down here. All heat is transferred to the water inside the calorimeter. There's no heat loss between the contents and the atmosphere. The maximum or minimum temperature is reached before any heat has been lost or gained to the atmosphere from the atmosphere. And I would say again, the other bit is that the heat capacity of the whole system is equal to that of water. So I'll just finish that bit off. So we have of system is equal to that of water, and no heat gained or lost to the environment. So it is all just the water. So the surroundings is just the water. And that's pretty much it. The other one said something about the temperature changing, maximum temperature reaching before it's lost any energy, but that is pretty much the same as this one here. Now, it says list the sources of systematic errors in calorimetry. Now, systematic errors are errors that are always going to affect every single result. So for one, it'll be that value there. So the fact that it's not actually going to be all the same as water, because you've got the glass stirring rod in there that's going to absorb some energy. You've got the thermometer. You've got the metal casing of the bomb calorimeter. You've got the what do you call it? The other bit, the styrofoam. So the source of error is leaking heat to atmosphere. So that means our temperature change. So our delta T is always smaller than ideal, because even if it's trying to decrease in temperature, if it's increasing in temperature, some of the heat is lost. If it's decreasing in temperature, some heat is gained by from the atmosphere. And heat capacity of system is less than that of pure water. So that, because most substances have a heat capacity lower than water, which means that they're going to change the overall heat capacity to a lower value. So that means the temperature is going to probably go up a little bit higher. Maybe the other way around. So we've got some extra things that are absorbing some energy, but either way, it's going to have an effect. And the last bit, so students in a class conducted the same experiment, but due to the inherent systematic errors, all calculated values, there should be calculated values, all calculated, I see, I'm misreading it. Students in a class conducted the same experiment, but due to the inherent systematic errors, all of them calculate differing values for the enthalpy of reaction. These are shown in the table below. Oh, one thing here. Mixing. Oh no, that's not going to work here. All right, that's a more random error. So they've got some values here. Indicate the number of significant figures shown in each of the student values. So we are going to look at each of these values and say the number of significant figures that we've got. We have 3 non-zero values, so that means we have 3 significant figures. This one here is 4 non-zero values, so they're going to be 4. Now this one here is ambiguous, so that means that it's not completely clear, because 400 is a legitimate number. Just because we say 400 doesn't make it any less of a value as 399 or 401. So this one here, we're not sure. If it was actually one significant figure, it could be 398 to one significant figure could be 400. So this one here is actually going to be 1 to 3. It could be 1, could be 3. We're not sure. If they wrote it in a different form, so if they wrote 4.00 times 10 to the power of 3, 10 to the power of 2, that would be 3 significant figures. If they wrote 4.0 times 10 to the power of 2, that would be 2. If they wrote 4 times 10 to the power of 2, that would be 1. So that's why scientific notation can be useful. And 400.65, every zero that is sandwiched between numbers is significant. So in this case, we have 5. So 400.65 is just as significant as 411.65. So we have 5 significant figures there. Cool. Hopefully that helps, like usual. And let me know if you have any questions regarding this stuff.